Hi everyone, welcome to our project, Ruby's Paracube. So first, this is the project background. So first question is how we represent the Rubik's Cube. We use the single master notation to denote the 18 possible transitions, as each of the 6 faces can be twisted 90, 180, and 270 degrees. The solver should take a series of scramble steps and output a series of solution steps, which is optimal. While the algorithms such as Distowitz can guarantee to solve every cube in 52 steps or less, it fails to give an optimal solution. For optimality, the search is often used. For shortest path, we are likely to come up with BFS search. However, given the high branching factors, memory will be the problem. And why do we use DFS instead? Because we visit repeated sets of cube states and never terminate.
Here's a brief illustration of the IDA star algorithm, which is, in more common terms, a bounded guess DFS. For n iteration, IDA star determines a bound. This bound is used to determine the set of leaf nodes of the current iteration search tree. If no solution is found in the current iteration, say I, the bound will be relaxed, so that more nodes will be searched in the next iteration. See the graph on the right. For iteration I plus 1, green edges are traversed in addition to the blue edges. The core pattern database is used to help determine the bounds in each iteration. Next, we have two sets of parallel implementations, one over OpenMP and the other using MPI. For parallelization using OpenMP, we have two main implementations. The first one is recursive. We mainly wanted to spawn enough tasks for load balancing. However, as we will explain last, spawning tasks at one level is not enough. There is not a perfect balance point between task spawning for load balance and the incurred serialization. This is given that the tasks may be of vastly different size due to pruning and heuristic guesses. Next, to allow for better task division and spawning, we created an iterative implementation with all problem states exposed to all workers. Workers may steal tasks as necessary to achieve better load balancing.
Our IDA star algorithm with MPI will generally be divided into two parts. So first phase would be the master node will be responsible for generating enough frontier nodes with best first search, where we expand nodes with smaller F value until we have enough frontier nodes, and then assign each frontier node to worker nodes for parallel searching. And after obtaining frontier nodes, the worker nodes will start sequential IDA start, and then report the searching bound back to the master node. In the case where the optimal solution was detected, the master node will abort. And here we are showing some results. The above two diagrams shows the speed of factors when the problem size scales. Test case T10 through T13 represent the problem with solution with depth of 10 to 13. The below two diagrams illustrate the interesting IDA-specific properties. Each of the 4 test cases below have solutions of depth 13. They differ in the number of nodes that the algorithm will search to find the solution in the final iteration. Interestingly, MPI scales better, but also have larger variance.
Lastly, parallelizing IDA star is hard. Here are the limiting properties of the algorithm that explains. For a given iteration, we have a bounded tree to search, GI. If GI contains the solution node, then the iteration is the final iteration. For the final iteration, the sequential algorithm will not search the entire GI. For the previous iterations where, say, GI-1 is searched, the amount of work is much less. Parallelization is often aiming for fewer dependencies. The stricter we want to follow the sequential algorithm, the more dependency we will create. Since the sequential IDA is a depth-first approach, while parallelization is inherently breadth-first. Breadth-first may cause some parallel workers to visit nodes that are not visited by the sequential algorithm. Given the graph on the right, sequential algorithm will finish the red tasks, continue on to the green task, find the solution, and return. The parallel algorithm will likely have some workers work on the blue tasks while one worker is working on the green task. Hence, the speed up is reduced. Also note that if we have n red tasks, they are very heavy. While the green task is pretty lightweight, we can imagine that having n plus 1 worker will provide superlinear speedup, since now not all of the red tasks are searched before the work on green task was able to find a solution. As a final note, fidelity between parallel implementation and the sequential implementation will benefit some search, but since we're not sure where the solution will hide in the tree, there's no point to enforce depth first over breadth first in the parallel implementation from